Hey everyone, welcome back to LabCoatz. As a home chemist, I found that there's exactly one thing that tends to ruin most of my fun. Restrictions. Sure, some restrictions are valid and well-intended, but way more are just based on terrible research or ignorance. For example, dichloromethane is mostly banned in the United States because, according to the EPA, it is a quote, deadly chemical. To their credit, people have died from inhaling extremely high amounts in an enclosed space. However, according to this reliable scientific source, doses as high as 185 milligrams per kilogram per day had no negative impacts on lab mice. For a 70 kilogram adult, that'd be over 10 grams of dichloromethane every day, with the LD50 already being eerily close to that of regular table salt. Does that sound deadly to you? Another chemical that could potentially be banned in the near future is sodium nitrite. This compound is extraordinarily versatile, being widely used to cure meat, preserve certain foods, and even help treat cyanide poisoning. So, why is it facing potential restriction? Well, how do I put this? It's because a few troubled individuals have made the unfortunate decision to, shall we say, purposefully ingest a lethal dose.
So, it's come to this.
Nitrites are a vital part of organic chemistry, and while pure samples are still available from select sites, they may not be forever. It is certainly possible to make nitrites, but the process usually involves heating large amounts of nitrate with either sulfur, charcoal, or lead. All things that would historically go into this frequently demonetized object. So today, I'll be showing how I managed to get a decent amount of nitrite from the one source that a ban will probably never touch. Meat curing salt. Specifically, preg powder number 1, which is over 6% sodium nitrite and can be bought for less than $10 a pound on Amazon. At first, my plan was to exploit the solubility of sodium nitrite in ethanol, and basically just extract it from the far less soluble sodium chloride. Admittedly, this method did work, but it was way too slow and inefficient for my taste. Processing the entire batch would have taken so much time and solvent that it really didn't seem worth the effort. After spending my day trying the extraction though, a thought hit me. Why extract the nitrite at all? Why not simply use the curing salt itself to perform chemical reactions? I mean, the only other compounds present are salt and a bit of red food dye, which should be fairly inert. And plus, using the salt directly could also make amateur syntheses a whole lot easier, at least if a major nitrite ban ever does end up passing. So, I decided to give it a try. For this experiment, I decided to try using my curing salt to make isopropyl nitrite, since it is one of the easiest organic nitrites to produce, and I'll actually be needing it for a few of my upcoming projects. To make this compound, I utilized the following reagents: 91% isopropyl alcohol, concentrated hydrochloric acid, and of course, preg powder. You can ignore the sodium hydroxide and ethanol. I thought I might be able to get sodium nitrite back if I reacted the isopropyl nitrite with sodium hydroxide, but as it turns out, this isn't actually very feasible. To get started, I first weighed out 500 grams of preg powder and added it to a large 1-liter boiling flask. Blending the salt could help expose more nitrite, but this is somewhat optional. Next, I added around 100 milliliters of isopropanol, followed by 50 milliliters of water. Then, to test it, I tried adding a bit of hydrochloric acid. Immediately, a lot of brown nitrogen dioxide fumes were released, and the red color of the solution quickly faded, which confirmed that there was indeed sodium nitrite in solution. So, I filled a pressure-equalized addition funnel with about 45 milliliters of the acid, hooked it up to the flask, and then carefully opened the valve as I swirled the mixture. Normally, I would use a magnetic stirrer to keep everything evenly mixed, but the slurry here was a bit too thick for that, so I had to do everything by hand. As the reaction progressed, the setup filled with a mixture of nitrogen oxides, which occasionally built up enough to pop the stopper off my addition funnel. Thankfully, this was about as bad as the process got. Otherwise, everything went relatively smoothly. Eventually, the red color completely vanished, and a bright yellow liquid collected at the surface. This was a mixture of isopropyl nitrite and leftover isopropanol, and to isolate the nitrite fraction, a simple distillation was carried out. At first, the solution only off-gassed a small amount of nitrogen dioxide, but soon enough, distillate began to rapidly pour over. Isopropyl nitrite boils at roughly 40 degrees Celsius, and it was the first fraction to come over. After carefully heating the mixture until the distillation slowed, I was left with 21 milliliters of a straw-colored liquid. Assuming the product was reasonably pure, this correlates to a yield of roughly 45%. Not awful, as per my usual, but definitely not amazing. So I decided to see if I could do better. I reran the procedure 2 more times, each time with slight variations. One attempt, which I'm calling the complete dissolution method, involved completely dissolving the curing salt in water, and then running the reaction like usual with the same amount of isopropanol and hydrochloric acid. My hope here was to access any nitrite that might have been trapped within the salt grains, and hopefully improve my yield. But this ultimately didn't work. Like most reactions, this is an equilibrium, and it just so happens that water is one of the products. By having a large excess of one of the products in solution, the reverse reaction becomes more favorable, leading to lower yields overall. In my case, I only got 37% of the theoretical maximum, which was noticeably worse than my first attempt. My best yield was actually achieved by using a curing salt solution that had been gradually boiled down and filtered of its precipitates. This process served to remove a lot of the unwanted water and less soluble salt, leaving behind a saturated nitrite solution which ended up giving me a yield of 52%. While this is technically an improvement, I don't know if it's enough to merit all the extra work. Still, this method does exist for anyone needing a 5 to 10% boost in output. At the end of the day, I obtained just shy of 40 milliliters of isopropyl nitrite from nearly a kilogram of curing salt. If I had been using pure sodium nitrite, I probably would have gotten twice as much for the amount of isopropanol used. But, considering this came from a product that most people can buy off the shelf at certain stores, I felt pretty good about it. At least we now know that curing salts are a viable source of sodium nitrite, at least for those without other options. Now, before I go, I want to quickly show what it's like to burn isopropyl nitrite. When placed onto an open dish, this compound begins to evaporate pretty fast, and when a flame is brought nearby, the vapors quickly catch. Isopropyl nitrite burns quickly with a clean, bright flame, similar to ordinary isopropanol, albeit with a somewhat more pronounced whitish halo. I was kind of expecting a more pale flame color, similar to nitromethane, but I guess that doesn't really befit this particular compound. The vapors do seem to burn with a grayish color though, so I tried capturing the ignition in slow motion, which did end up looking pretty cool. Alright, I think that's basically it. I'll be converting my isopropyl nitrite into sodium azide, which I plan to make into something a little more explosive. I don't want to give too much away yet, since the synthesis could always fail, but let's just say this compound has a higher nitrogen to carbon ratio than azido-azide-azide. More details coming soon. A special thanks goes out to all the existing LabCoatz supporters. Without their help, this channel probably wouldn't be as close as it is to cracking 100,000 subscribers. Remember to like, share, and subscribe, and I'll catch you next time. LabCoatz out.